Hello, my name is Junhong from Indiana University. Today I'm going to present our ICRA 2023 paper, Causal Inference for Efficient Autonomous Motion Planning with Observational Data. This work is collaborated with Expedia Group and Army Research Lab. Efficient motion planning requires the robot to compare action outcomes, which is hard to handcraft in unstructured environments and requires data-driven methods. Given task and safety constraints, robots must rely on observational data acquired from other robotic missions rather than random exploration. However, the inherent biases within offline data collection process makes the motion estimation inaccurate. Our research seeks to mitigate such biases during the motion estimation through the application of causal inference for better motion planning and control. To understand the challenge of learning from offline data, we use a hypothetical scenario involving learning from human driving dataset. This dataset records collision rates and obstacle distances, classified as dangerous, precautionary, or safe. The dataset reveals that human drivers use more hard braking to avoid collisions with close obstacles and use more gentle braking in safe situations. Suppose that the self-driving vehicle uses this dataset to decide which action to take under the precautionary situation. A simple approach involves computing the average outcomes for both actions. This method, however, yields a counterintuitive estimation. The collision probability for hard braking is higher than that for gentle braking. Consequently, the autonomous vehicle may select the gentle braking to minimize collision risk. Intuitively, this decision appears to be flawed. The central cause of this problem lies in the presence of confounding factors. In this example, the confounding factor is the distance, which influences both the action and the outcome. In fact, the higher collision probability observed with hard braking could be attributed to the shorter distances when braking is taken, rather than braking strategy itself. If we could observe all the outcomes associated with each data point, we could break the causal relation from distance to action. The estimation would be more accurate. However, in practice, this is not feasible due to the safety concerns. The regression model mentioned earlier for predicting outcomes cannot address the bias presented in the observational dataset, leading to inaccurate predictions and suboptimal decision-making. Our first contribution is to employ the debiasing capabilities offered by causal inference. It balances data points by reasoning over the data generation process. This approach can mitigate action selection bias, improving prediction accuracy for downstream decision-making. On the other hand, offline model-based reinforcement learning also aims to use the offline dataset. In contrast to our proposed method, this approach penalizes state action pairs that lie outside of the data support, preventing the agent from encountering these state action pairs. However, the bias persists when predictions are made within the support. As our second contribution, we propose integrating causal inference with offline RL. This approach facilitates safe and efficient action within and beyond the data regions, addressing the limitations of both techniques. Our first method is called inverse propensity weighting. The primary goal of IPW is to balance the dataset to reduce the dependency of the action on the observed state. This is achieved by multiplying the action outcome by its corresponding inverse action probability, or inverse propensity score. In this way, the data is reweighted to simulate a pseudo-population in which the confounding biases due to the states are minimized, allowing for more accurate and reliable causal effect estimation. However, there are times when the data is too complex and the propensity score model cannot align with the true data functional form. In this case, we can combine the IPW result with the regression model. This can ensure that when either of the regression or propensity score model is correct, we can have a consistent and unbiased result. In the experiments, we use PyBullet to simulate a car racing scenario under different masses, where reduced mass results in more slippery motion. The ICRA policy intervenes when the vehicle slips to ensure safety. We compare causal inference and combined methods against model-free and offline model-based RL. Qualitatively, as shown in the video, we observed that causal inference-based method can successfully perform the task. In comparison, the standard regression model steers the vehicle off the track. The table also shows that the combined method can utilize the strength from both offline RL and causal inference to outperform all other methods in the experiment. We further scale up the proposed method to a real-world navigation scenario on an unstructured, uneven dirt terrain. We use a high-dimensional observation with 10 by 10 elevation map. The goal of the vehicle is to traverse 3 waypoints with approximately 50 meters in distance. The observational data is gathered by a human operator maneuvering a ground vehicle through 3 waypoints. The operator is instructed to either maintain a low linear velocity on highly elevated terrains or avoid them entirely. The dataset bias stems from the operator's inclination to comply with these instructions, skewing the data towards a particular driving behavior when encountering elevated terrain conditions. As illustrated in the video, even with the presence of a biased motion dataset, the vehicle can still conclude that highly elevated terrains pose a potential hazard, and thus opts for less aggressive actions to prevent overturning on such terrains. Overall, our work establishes the connection between causal inference and robotics via debiasing offline datasets. The more robust performance compared to the standard regression model suggests that the careful reasoning over the offline data generation process is necessary for safe and efficient decision-making in robotics.